Hello, everyone. I'm Auritra Ghosh. I'm one of the Catalyst Fellows at the University of Washington, and today I'm talking to all of you about the power of machine learning and robust statistics in galaxy evolution. Now, in order to present this topic, I could have probably picked any subpart of galaxy evolution, but I will be talking to all of you about galaxy structure. And as many people have made the point already, galaxy structure plays an important role in us understanding galaxy formation and evolution. Since the many decades, astronomers have linked galaxy structure to many fundamental properties of the galaxy, as well as that of its environment. And importantly, all these different correlations have proved to be very powerful tools in assisting us to investigate the intricacies of galaxy formation and evolution. And if you ask the question, well, why is that the case? From a very simplistic model of the hierarchical model of galaxy formation as we know it, we see that the structure of a galaxy changes almost at every step of this hierarchical process. And therefore, you can use galaxy structure as a powerful probe of both dark matter halos as well as the baryonic processes that go on inside them. Now, out of all these correlations, the one thing that I will focus on today is specifically the relationship between galaxy structure and environment. Now, as all of you know, we have known for quite a while that denser environments usually have more massive galaxies. And we also know that denser environments usually have more bulge-dominated or passive galaxies. But what about galaxy size? Do denser environments have larger galaxies or smaller galaxies? As all of you know, galaxy size is primarily set by the stellar mass of the galaxy. So the correct question to ask might be, does environment play a role independent of stellar mass and morphology? I can reframe the question to ask essentially, if we take two galaxies of the same mass and similar morphology, but in two different environments, one in a denser environment, one in a less dense region of the universe, which one happens to be larger? Now, we are definitely not the first people to ask this question. Many people have asked this question in the past. And there has been a lot of disagreement about the answer. So this is a table showing many different works that has been done over the last decade on this topic. And if you focus your attention on the extreme right column, you will see that people have found all kinds of answers. They have found positive correlation, they have found negative correlation, they have found no correlation. Now, if you ask the question, but why is that the case? Why have people found such different varied answers? If you ask that, you get a hint by looking at the sample sizes. So till now, it has only been possible to study only limited sample sizes. But that is not the only reason. So small sample sizes, absence of robust uncertainty measurements on the effective radii, not using statistically robust techniques to assess the presence of correlation, and also not being able to control for various nuisance parameters. So these are techniques which have prevented us from getting an answer to these large questions. So what I argue we need is we need a large uniform sample. We need effectively large sample of effective radii measurements with accurate uncertainties, and also machine learning frameworks which can analyze such large data volumes. And of course, Rubin LSST with its over its 10-year program and also with intermediate data releases will give us such large data volumes. But as many people have made the point, even now it is possible to make a dent on such questions using LSST precursor surveys like Hypersupreme CAM. And I'm going to do the same thing. What I'm going to do is from here on for the rest of the talk, talk about how we can get at some of these questions with existing Hypersupreme CAM data. So for this work, what we do is we start with a sample using our HSC structural parameter catalog, which has about 8 million galaxies up till redshift 0.75. These structural parameters were obtained using the galaxy morphology posterior estimation network. So this is, we have tested out GAMPen against traditional light profile fitting codes, both on simulated data as well as real data. And we have shown that not only do we get accurate structural parameters, but our posteriors are about 70 to 80% better than what you get from light profile fitting codes. And we start with these structural parameters and we correlate them with the Hypersupreme CAM density catalog, which essentially has number counts measured using top hat aperture distributions. And we correlate these two catalogs, and we end up with a sample of about, oh, let me go back. And we end up with a sample of 3 million galaxies down to stellar mass. We are complete till a stellar mass of 10 to the power 9. And most importantly, what we are able to do is, because we are using such a large volume, we're able to increase our sample size about 100 to 10,000 times compared to previous studies. Now, once we have this, how do we study the correlation? So the first set of plots that we use are these effective radii versus environment. So on the x-axis, you have overdensity. Positive numbers mean more denser regions of the universe. Negative numbers mean less dense regions. And as you will see, we are plotting delta RE. So delta RE is essentially just tells you how much a galaxy is large compared to the median radius for the specific stellar mass and bulge to total light ratio. So controlling for mass and morphology, like I was mentioning in the beginning. And what we have is that I'm showing this to you for the first redshift slice. We have 4 different redshift slices. And as you will see, this is the result plotted out for the 4 slices. And instead of trying to judge whether a correlation is present or not just by visually looking at it, we can do better because I'm showing you just the median point with a typical error bar. But essentially for each of these points, I have hundreds of thousands of galaxies with full posterior distributions of the effective radii available. So what I can go ahead and do is that we can draw samples from each of these posteriors. So we draw 5,000 different samples. And what this effectively does is it creates 5,000 different stochastic versions of the same data set. Now what I can do is that with these different versions, I can run Spearman's rank correlation test. And depending on the results, I can try to decide whether I can reject the null hypothesis of null correlation with more than 5 sigma confidence. And when we run this test on each of these redshift slices, I'm with a check mark. The green check marks are for the heavier sample. The orange check marks are for the slightly less massive sample. What we find is that we can confirm the presence of the correlation for almost the entire sample. Galaxies in denser environments appear to be up to 25% larger compared to their less dense counterparts. The strength of the correlation, we see a significant change in reduction in the strength of the correlation coefficient beyond redshift 0.5. And we also see that for the heavier sample, we are able to confirm the correlation throughout the entire population that we have. Another way to look at the exact same question is through size mass diagrams. So here on the y-axis, you have galaxy size. On the x-axis, you have stellar mass. And the dotted line is showing the median trend, and the colored points are showing you specific galaxies in specific environments. And the delta RE panel at the bottom is showing you how the points deviate from the median trend when you hold stellar mass and morphology constant. And what you find is that consistently, galaxies in dense environments are larger. So you're seeing the same effect. And again, if I plot this out to higher redshift slices, you see that the effect seems to flatten out in them. But here we see an interesting thing happening, that even in the 2 higher redshift slices, beyond a stellar mass of 2 10 to the power 11, we see again the presence of a strong correlation. And even though this is towards the very end, we have enough statistics down there to kind of show this result. Now, all these results I showed you were for the entire sample of galaxies. If I split them up into different subsamples based on star formation or their morphology and show you whether we can confirm the correlation or not, you will see that even within each subpopulation, we are able to confirm the correlation, and the results follow the similar trend as we saw in the overall sample. That is strongest in the lowest redshift bin and then weakens out in the last redshift bin. Now, you may ask the question, okay, why do we see these results? So there is no trivial explanation for all the observed correlations that we see, but it's possible to kind of tease it. So what this really shows is that we need more understanding of how the structural parameters of galaxies are connected to their dark matter halos. But just to throw out some ideas of what might possibly explain these results, one set of things is that if in the halo spin plays a role in setting the size of the galaxy through the virial radius. Then we also know that halos with higher spin cluster more strongly. Then that can provide you some explanation of this effect for disk-dominated galaxies. On the other hand, for the ellipticals and the bulge-dominated galaxies, and to explain the existence of the critical stellar mass, one thing which might be able to do this is many people, or some people have predicted that mergers are more efficient in denser environments. And we think that could be one of the explanations for the bulge-dominated sample as well as for the critical stellar mass. So summarizing, what we see is that this is a study which kind of tries to move the field forward, in which there has been a lot of disagreement. We show with more than 5 sigma confidence that galaxies in denser environments are up to 25% larger. I will leave you with the intricacies of the details we find and a picture of my collaborators. Thank you.
Questions for Aritra?
So the one trick that's tricky with a larger sample is the ability to do the stellar kinematics, and that rise up at high mass is probably associated with the transition from rapid rotation to slow rotation, gas, in the systems, gas not in systems. And so the physics of the merger, star formation may have a kink right where you see that going up between giant ellipticals and spirals and what have you.
Yeah, that might be the explanation of the fact. And I think one of the ways that we might be able to tell the exact reasons of why we see these things would be the hard thing for us was to find an existing simulated sample which matches our data very closely. So the idea is that we can try to create a simulated sample which closely mimics our data, radiative transfer them, create the images, and then run the same algorithm, the same reduction pipeline on those radiative transferred images, which will hopefully, where we'll be able to tell what exactly is causing these different things, whether it's a dynamical effect or a different thing.
May I ask a question from Zoom?
Very quickly.
Yes, thank you. If you add LSST data for 10 years, how much better are you going to get than these already impressive results?
Hard to tell from out of the box without adding anything, but I think my answer will be to think more of this in terms of my first slide where I was showing all these different correlations. So essentially, I think we can still, you have to remember, see that we are doing this only till, let's say, magnitude 23rd. If you add 10 years of LSST data, how deeper can you go? And when you go deeper, does the correlations remain same or not? So essentially, extending the parameter space that we explore, that's what I hope over 10 years of LSST, what will do better for this specific problem.
Thank you.